Okay, so we have one question here. The question is, we measure the shear stress by changing shear rate for different samples, sample 1, sample 2, sample 3. Based on this data that it's measuring by a rheometer, uh, can you guess which pattern, which model, which flow behavior uh, is described each of the samples? Uh, so um, for this reason, because I want to find the pattern, the best way is to drawing or plotting the shear stress and shear rate in um, in a chart. So the first question is about the finding the pattern. So for the drawing or plotting, we need to plot the shear stress versus shear rate. Shear rate is changing by is independent variable, and shear stress is dependent variable. So we are going to draw or plot uh, shear stress over shear rate. First, click on far away from your data. For example, here, going to insert chart. As you remember, um, we use the scatter for x and y because we have the pair data here, x and y. So we just put the scatter, select the scatter, just dot. We need to put the paired, I want to check the pair data. Okay. And now I have one empty space for drawing or plotting the graphs. I want to draw for sample 1. Okay, so just right click on the white space, right click on white space in the chart and select data, add uh, data. Yeah, series name, I want to choose sample 1 for the series name, and x value is our independent variable, the shear rate, and the dependent variable is shear stress. For example, we choose. So that's all. You can see. Okay, as you know, I hate this line. I remove. Okay, that's all. So now you can guess this pattern is what? Somebody can guess? Sample 1 is which pattern? You can open your microphone and let me know. Which pattern is this one? Bingham. No, it's started from 0. Bingham have some shear stress here. I want to name the yeah, Newtonian. Yeah, yeah, it's Newtonian. You can see here. I want to name the chart. Chart. Okay, axis title. I want to put axis. This is shear rate. Shear rate. And this one is shear stress. Don't forget to put the this is Pascal, and shear rate is is second on second minus 1, or you can put 1 over second. 1 over second. Now we can see we have this pattern. This pattern is a Newtonian shear stress equal to a slope, and it's started exactly from 0. You can see at 0 shear rate, the shear stress is 0. If it's not 0 here, it means that it have some yield stress. So if have yield stress and a linear, it will be Bingham. But this one have not any yield stress, so it's Newtonian. Can you guess the viscosity of this one? Viscosity of this material? Yeah, it's easy. If you remember, we are going to add a trend line and linear. Okay, linear. Here, display equation on chart. Okay, and the R square. See, um, here we have y is equal to 0.4 x, and R square is exactly 1. Means that all of the data is in one line. So this material is Newtonian, and as you remember from a formula, sigma is equal to mu gamma, and mu was be the viscosity. So what is the viscosity of the sample 1? The viscosity is 0.4. So the viscosity of the Newtonian is coming from this one, 0.4. The viscosity is 0.4. So again, we can draw for the next one, for the sample 2. Okay, again we draw for sample 2. We can add here, or maybe we can, okay, I want to draw another one to teach you again. So I want to draw for sample 2. Okay, going to the insert, scatter, and an empty space is appear here. I'm going to choose, okay, add series name. This series name is sample 2. X is coming from the shear rate, and shear stress, I remove the data for shear stress, and then put this one, choose this one. Okay, now you can guess this pattern. You can guess this pattern. You can guess this pattern. What's the pattern? You can reply in the chat box. This pattern is, you remember, shear thinning, shear thickening, Bingham. Can you guess? You remember? Yeah, Farad. Yeah, it's shear thinning. This pattern is shear thinning, starting from 0 and going to up with this one. So this is a second one, second sample. and I want to draw for the third sample. Okay, again, I take it here. Okay, I will show you later the pattern and describe more. And I want to know about the third sample. Insert again. Um, Coming to the scatter, empty space is here. Again, right click, select data, add. Series name, this one is sample 3. So x axis is shear rate and y axis is shear stress. Okay, that's all. That's it. Yeah, okay. This pattern is, please guess. This pattern. This pattern is for become. Oh yeah, wait, yeah, that's correct. It's shear thickening. Yeah, this pattern is shear thickening. I want to write something here. Let me recall you that you remember the formula for the uh, yeah yeah, you need to wait, yeah, you need to check again, and something need to more practice. um, you remember the formula of the equation, um, sigma shear stress equal to shear equal to uh, a constant, um, and gamma dot, you remember gamma dot. I want to put the gamma dot power n. You remember this model? Yeah, this model is for power law model. We call the K as the uh, viscosity consistency. This one is K, viscosity consistency, and N is the viscosity index, consistency coefficient, and this one is the viscosity index, the N. So sigma is shear stress and gamma is shear rate. Now you know this model. I want to ask you, for Newtonian, you remembered for Newtonian, K is mu and N is 1. If you remember, for the this is for power law. You remember for power law, and for Newtonian, I want to again one. Okay, I can start by the sigma is equal to mu. Mu, mu here is viscosity. Mu gamma power 1. This is the, you remember the Newtonian. Okay. This model is Newtonian and this model is power law. And also for the Bingham, you remember for the Bingham, I want to this one for Bingham. You remember? sigma for Bingham equal to sigma 0, sigma 0 plus k gamma. This is the Bingham plastic. Okay, so we have these three different model. Sigma is equal to k y power n. This one, the Newtonian, sigma is equal to mu and multiplied by gamma. Gamma is shear rate. For this one, for Bingham, sigma is equal to sigma 0. Sigma 0 is the what we call the sigma yield stress. Yield stress plus k gamma. This one. So here we have this three model, different model. Based on this three different model here, if you remember, we have this three. Okay, we have this three. The first one is the Newtonian. I want to bring the samples down. Okay, this is a Newtonian. Y is sigma and x is the gamma. So the mu is here. We can easily find for Newtonian by simple way. We can easily find the viscosity. The viscosity of the sample is 0.4. For second sample, if for the second sample, if we want to find the viscosity index and the consistency coefficient, viscosity index, this one is viscosity index n, and k is consistency coefficient. It's like sometimes viscosity, but this is not a viscosity, this is a consistency coefficient. So if you are looking for k and n, how you can find k and n by this data? How you can find k and n? You remember the last session on the model fitting? Yeah, okay. We can easily fit the model. How we fit the model? Okay, I just bring the sample down. I just want to focus on sample 2 to measuring the okay, the sample. I want to calculate k and n. K and n, what's the k and n? K is consistency index and n is the viscosity index. So consistency coefficient and viscosity index k and n. I want to calculate these two, k and n, based on the data coming from. Okay, for sample 2, this is the practical data. We need to calculate the I want to put the k and n, k and n. K and n. I have put it k and k. I want to start from 1 and n also 1. For this one, I want to use for sample 2. Sample 2. Okay. a K and N for this. I'm going to for sample to ST. I want to put the ST theoretical. How we calculate the theoretical sample from this model? You can see sigma shear stress is equal to K shear rate power N. So I am calculating based on this. So this one is equal to K multiply by shear rate power N. This one. If I want to copy and paste to the next one, because I'm using the K and N as fixed number, so need to spend some money here. Before and after J, I put the dollar sign. Okay, to fix the J2 and J2 and J3 is referred to K and okay. Then copy and paste all. Now I have this data K and N. You can see I have this data from theoretical for sample 2 ST2. This is you remember this is this data coming from practical, is coming from theoretical from this one. Now I want to calculate the differences between SP for 2 minus ST2 and power 2. So it's equal, don't forget to put equal, bracket open, the practical data minus theoretical data, then close and power 2. Okay, now this one copy and paste to all, and then going to sum up. How to sum? I have how to sum, and I want to minimize this list doing the list score to minimize the this one okay, I want to minimize this summation by changing these two, okay, using the solver from data, using the solver, and I want to minimize F24. You can also reset all if you want, and then measure. Objective is the summation. You want to minimize, maximize, or you want to reach a value, you want to minimize. Minimize F24 by changing which variables is to one. Okay, so then solve. Yeah, exactly reach to, can see, reach to 0. Means that, okay, K is 1.39 and N is 0.71. I want to draw this one. I want to put again this one 1 and this one 1. Again, I want to draw and show you what will happen. This one is ST2, theoretical data for sample 2. The X is same and the Y is coming from the theoretical data. You can see we have this orange one. This is I want to fit this one. So when it's fitting, you can see when we are going to fit using the data solver, because I didn't change anything. Solver, and you can see what will happen here when I press the solve. You can see all the data from theoretical and practical exactly on one line. How? By this. And this is confirmed that our regression is complete. So the consistency coefficient is 1.39 and N viscosity index is 0.71. Don't forget that in this model, in the power law model, sorry, in the power law model, in the power law model, if N is equal to 1, exactly it will be Newton. If N is lower than 1, it will be shear thinning. N is lower than 1, it will be shear thinning. If N is higher than 1, if N higher than 1, it will be shear thickening. So we suppose to, if we draw this one for the sample 3, for sample 3, the third sample, I'm bringing the third sample here. Close. My system is almost low. Okay, not going to close. Never mind. Okay, for sample 3, I want to do it for sample 3. So, uh, as I want to repeat that if N is lower than 1, it will be shear thinning. If it's higher than 1, it will be shear thickening. This is shear thickening. So we are supposed to reach an N above 1. So we are going to calculate this one for sample 3. For sample 3, I want to do it again. I want to keep, you want me to keep this data? It's okay. Now I'm going to calculate ST3, means sample 3 theoretical data. It's equal to, sample 3 is equal to, you remember, K. Okay, so put for sample 3. Okay, again I start by 1 and 1. This one is equal to K. This K in is the K multiplied by shear rate power n. Okay, just fix the data, fix the constant by spending some money. Before and after, just the letter, not the whole. Before and after. Okay, okay. Next, copy and paste here. And I want to draw this one for you. add series name. I want to ST3 and X is same. Y is here. You can see. This is the line. You know why this is a line? Because I put the n as equal to 1. 1 is very good starting point for solving the rheological problem. So I put the 1 for n and k also, and I just assume. No, this is not same as this data. I want to change this data to exactly cover. How? By changing this sample. So for this reason, I need to calculate SP3 minus ST3 power 2 is equal to SP3. This is the SP3 minus ST3 and power 2. Okay, now copy, paste all. Now I want to add, use the summation. How to sum? I sum all of this data. Now I want to do a least square, meaning that by changing these two k and n, by changing these two, I want to minimize the square of the differences between practical data and theoretical data. Now going to do data by solver. I want to reset the solver. Okay, my objective is here H24. I want to minimize H24 by changing this K and N. Okay, that's all. Now you can see what will happen here. Yes, exactly again come together. Now you can see here the K is almost 0.01 or maybe 0.09999. If I instead I put this one as 0.01 and the N is equal to 1.82. As I told you, in the shear thickening, N is above 1. For shear thinning is less than. This is more than 1, it's less than. And if it's Newtonian, the Newtonian, it's exactly the N is equal to 1 and K is the consistency. So this is one of the using of model fitting to find the viscosity, everything here. So another question here arises that can you compare the here for the non-Newtonian we have not viscosity, we have apparent viscosity. Apparent viscosity means that it's in a special shear rate. If we connect this point to the to the 0 and 0, so if we connect, the slope of this line will be our apparent viscosity. So if we want to compare the viscosity, it's dependent which shear rate. We cannot exactly say which of them. If I want to compare, these three samples. I want to compare sample 1, 2, and 3. and recognize that which is have higher viscosity. So in this case, I need to draw all of the data in one figure, sample 1, 2, and 3. The shear stress of all of the sample together, one shear rate in the same shear rate, and then compare. So here I want to again insert chart and scatter, and this time I want to put line because I want to scatter and line. It's up to you. It's up to you. It's not compulsory to following exact my way. Right click here, then select data, add. We have sample 1. X series is here. The shear rate is X series, and Y is we need to remove this one, and Y is a shear stress. Okay, the first one. Want to add the second one, sample 2. Same shear rate and shear stress is different. Okay, then add another one, sample 3. Shear rate is same for X, and shear stress we can draw from here. Okay, that's all. And we can put the legend. See the horizontal line and vertical line. This one I prefer to bring it here. Okay, so sample 1, sample 2, sample 3. If I want to compare the viscosity of these three materials, it's depend. You know, uh, in around maybe around 90, around 90, between 80, between the 80 to 90, all of these three at same shear rate, we have exactly same shear stress. As you as the definition, the division of shear stress to shear rate is should be viscosity. So here you can see at this exact amount they have same viscosity and same apparent viscosity. For Newtonian, we use exact viscosity. For the non-Newtonian, we use apparent viscosity. At lower here, you can see here, the viscosity of shear thinning is lower than Newtonian, and after that is shear thinning. But when we are going above shear rate higher than 100, higher than 90 around, you can see it will be changed. The amount of viscosity for shear thinning is less than Newtonian, and it is less than shear thickening. So for comparison of the viscosity of different type of material, we need to draw the shear stress over shear rate and then compare. And in different shear rate, you can see in lower shear rate, the viscosity of shear thinning is higher than Newtonian, and after that is the viscosity of as we call this one, viscosity of shear thickening. Here it's opposite. Shear thickening is higher than Newtonian, and then shear thinning. It's depend on which shear rate you want to measure. It will be like this one. Okay. If we have one, don't forget this one. If we have one Bingham, don't forget that if the Bingham is higher, the slope is important for us. For this reason, if you want to compare Bingham material with this one, you need to decrease the yield stress and starting your material from here to compare. If you want to compare the Bingham with this different with this power law, shear thickening, and Newtonian, you need to uh, decrease the shear the yield stress and starting drawing from here and then compare. Don't forget this one. Maybe sometime you confuse. If it's drawing from here, the viscosity is higher. No, viscosity is not higher. The starting point is higher, so need to decrease and then draw from here. If it starting by, for example, 100, you need to decrease 100 from all of the data. And again, if you want to compare, not at the first time, if you want to compare, it's better to instead of the drawing from here, it should be draw from 0. Okay, so this is the remaining things that maybe help you to responding to the question and also solve a final exam. You need to know about the this data here. Okay, so one more thing here. Okay, you any question here? Any question on modeling? I will upload the file on my YouTube channel. Please come and see again over there. If you have any question also whether you can ask in the comment section or also you can ask me from here. Any question? Going to the now I want to take around maybe okay. So the last part about the thermal properties and especially on the uh, DSC, especially on DSC. So it's coming 3. Okay. So I want to describe something about the DSA analysis. Please read through the um, handouts, check everything over there, and also watch the Prof. Karim video that I have shared with you to learn the basic things. But here I want to just describe something about the DSC chart. DSC is differential scanning calorimetry that useful to measuring the uh, measuring the thermal properties. Thermal properties of material is mostly dividing in two types. One type of the thermal properties um, is first order transition. Another one is second order transition. You already know the pattern of the first order and second order. In the first order, like melting or crystallization, we change the phase like ice to water or water to water vapor. It is exactly first order. during the first order transition, temperature is fixed, but in the second order transition, like the changing from the amorph to the rubbery, is the temperature will be changed during the transition. Um, so how we can measure and detect by DSC? We can detect. This is a pattern of a DSC. I will share this chapter in this book chapter. It's a free book chapter about some food analysis. You can again, I will upload in e-learning system this one. You can check this chapter about DSC. Um, in the DSC pattern, when we want to measure thermal properties, we put some amount, a small amount of sample in the pan and start to heating from a certain temperature to the final temperature. Mostly for food material, we are starting from uh, 10 to 20. 10 to 20 we are starting and going to up around 200 in DSC. It's depend the maximum and minimum temperature for your different material, but the range is starting mostly from around 0 to 20, the room temperature going to around 200 degree. In a DSC pattern, uh, and the DSC will measure the heat flow. You know, as a rheology, we change the shear rate and measure shear stress. Here we change the temperature and measure the heat flow, amount of heat that need or release from a sample. Uh, we measure and it reported as one graph or maybe as a data. Okay, how we can detect which transition will occur? Um, this I just mentioned. This is the glass transition temperature here. This is one glass transition temperature here. This is a crystallization occur here, and one melting we have here. This is melting, this is crystallization, and this one is the glass transition. What's the difference between these three patterns? No, this pattern and this pattern is opposite. Here, wrote that exo up means that if it's exothermic, the peak appear to up, and if it's endothermic, it will be appear the peak will be down. So if the peak is up, it's exothermic. This is an exothermic transition, and this one is endothermic transition. It starts from one point going up and then again back to same point. You can see exact same point going up and then back. This one also going down and again exactly back to the same point. Down, this is up. But this one is going down but never back to the first point. Yeah, to detect the first order and second order in the DSC pattern, if a material is in crystal form, it have not shown any like this one. This is for crystal material. This one for amorph. This one for crystal material. Crystal part here. So uh, the first order in the pattern, the first order exactly starting from same point, going up or down, and then finish at the same point. Starting same point, going up, and then back to the same first level. Here also you can see going up. This is the first transition, first order transition, first order. If it's up, this is crystallization. If it's down, it's melting, because for the melting you need heat. It is endothermic. But in crystallization, it's exothermic. During the crystallization, it's exothermic. And if we have second order transition here, you can see we start from one point going down, but it cannot back to the first point. This is the TG, glass transition, or second order. So just if you want to check, or maybe you want to recognize different material uh, based on the DSC pattern, if the material like this one, it have TG, glass transition, it's TG, rubbery material to glassy, rubbery to glassy. But this one and this one is first order, like crystallization and melting. If you have a rubbery material, or you have, by heating it start to flowing, this one will happen. And like chocolate, you put the chocolate in your mouth, it start to melting. It's not melting, it's start to phase, first order transition, changing the increasing the temperature above TG. But if you put ice in your mouth, it's, it will be like this one, exactly like this one. Chocolate, or maybe this one sometimes strawberry thing. This one is glassy thing, or maybe something like crystal. Crystal. If you put the crystal ice in your mouth, it will be happen like this one exactly. But the chocolate is not back to the first position. Okay, yeah, I just want to describe the DSC application and how the pattern will be different. If you recognize that in a sample, it uh, it was happening first order, you need to mention that the first order will happen. If it recognize that your sample have TG or have second order, like this one, depend. This is also first order. Crystallization also same as the melting is first order, but the glass transition is not the exact same. So for today is almost finished. Uh, just I want to ask you again two things. Please check all the handouts. Watch the YouTube video from Prof. Karim, and also please. And second thing, please don't forget to fill the form of course assessment. Please, if you forget for both course, please do. I found that some of you forget. Please, Jingming, please um, say the student and also inform them to fill the course assessment uh, evaluation. I will upload the video part, and if you have any question, you can ask me here. Now I am around 15 minutes will be here. And if you have not any question, you can leave the chat and enjoy your time. I stop the record and I will upload this video on my YouTube channel. You can watch this video and the previous video on my YouTube channel. Okay, don't forget to, if you are interested to my um, content, I will maybe later I'm making some video about some um, modeling and simulation in food engineering. If you are interested, you can subscribe to my channel and receive the notification about my files. Okay, so when I stop the recorder and say here bye bye, but with you,